You have probably already looked at different ways of identifying reactions. We've had synthesis reactions, double displacement, single displacement, things like that. There are other ways to classify reactions. Think about something called an acid-base reaction or combustion reaction, where you're paying attention to the things that are reacting rather than how atoms rearrange. Redox chemistry is another way of doing that. Now we're going to start with what that means, but I want you to think about a few reactions, different types that we've seen. And if I asked you to identify, to examine these and decide what all of these reactions had in common, it's not quite that obvious, so you might have a hard time doing it. And if I gave you another reaction set, it's quite different. And what's different about it? It would probably take you a while, again, because it's not obvious. But if I told you that the first three reactions were redox, well, that doesn't really help until we know what redox means. So what does redox mean? Now I'm going to give you some background that you don't need to write down, but a little bit about where these terms come from. It actually, the reduction, and that's the part, I guess the red part of redox, comes from the word reduction, and that comes from metallurgy. And if you think about how that would happen back in the day, you would scoop out an ore, and an ore containing some metal that you want is usually in the form of an oxide. And then what you would do is you would do something to it to reduce it to the metal. Now the word reduce, if you think about the mass there, the amount of mass of ore, in this case iron 3 oxide, that I put in, I'm going to get a smaller mass of iron out because I've taken the oxygen away. Now I may or may not have known that, but what I do know is the amount of stuff that I put in and the amount of stuff that I get out seems different. The other half, 2/5 of the word redox, the ox part, comes from the word oxidation. Back in the day, it was understood to be a reaction with metal. So in other words, the opposite case. If I take that iron now and I react it with oxygen, it will oxidize to the oxide of iron, iron 3 oxide. But we also realized that very similar things were happening with atoms other than oxygen. So the bottom example here where the iron is reacting with chlorine is also considered to be an oxidation type reaction, even though the word oxidation is being more broadly applied. Okay, what are we talking about when we call something a redox reaction? The modern chemistry understanding of a redox reaction is a reaction where you have the change in an oxidation state. Now, an oxidation state is similar to an ionic charge, but more broad. So, for an ionic bond between a metal and a non-metal, the oxidation state and what I would have called the ionic charge are going to be the same. But if I'm talking about non-metal bonds, now I'm not talking about ionic bonds, I can still apply the term oxidation state. So for this one, sodium starts out as a neutral atom, reacts to form a +1. Chlorine starts out as a neutral diatomic molecule and becomes a -1. So that formation of the ionic charge, I can now say that's a change in oxidation state. So when we talk about reduction, what we're talking about is a gain of electrons, and that's going to make the oxidation number go down. So chlorine in the previous slide was starting from 0 and going down to -1. That's a reduction. Pay attention though, because reduction happens when you gain electrons. So we're losing oxidation state, or we're going down in oxidation number, but we're going up in electrons, which makes oxidation going to be the opposite process, or makes oxidation to be the opposite process if I want to speak English. And that's going to be the loss of electrons, but it's going to be going up in oxidation number. So if we think about a number line, as I add more electrons, or let's take away electrons first, I'm going to be taking away negative charge. The resulting thing is going to become more positive. If I throw more negative charges on, that resulting thing will become more negative. So I'm going up in oxidation number, down in oxidation number. Well, how do you get the oxidation number? Well, in some cases, it's going to be pretty apparent, as I said before, the ionic charge. But now, to make it more broad, if we assume that everything is ionic, and it's not, but in terms of bookkeeping, in terms of identifying oxidation numbers, we kind of pretend that if it were, what would the charge be? And then that means electrons are going to go to the more electronegative element. Now we're not going to have to worry about things getting really crazy and like needing electronegativity numbers. But if I take a look at a chart here and try to map out some that are pretty common and fairly standardized. Any unreacted element that's not in a compound, that's not formed an ion, will automatically be an oxidation number of 0. It's neutral. Any monatomic ion, so chloride, oxide, sodium ion, potassium ion, those will be whatever the charge is. So I've got an aluminum +3. So that's all stuff that you've known for a long time. Hydrogen in most compounds we will assume to be or treat it as an oxidation number of +1, not an ionic charge necessarily, but an oxidation number of -1. Now for us, that's all we're going to care about. But I said most compounds, so the rare exceptions, which are not going to apply for us in this course, it could sometimes be a -1 in a compound. You're not going to see that, so you don't need to write that. Oxygen is another one that we can count on in almost all cases. Again, I've got most, so it's going to be -2, and again, that is fairly familiar. Doesn't really mean we have to learn something new. And then the exception to that, which we aren't really going to need, is being -1 in the case of something like this last example, which is hydrogen peroxide. There's probably one more example where oxygen is not becoming a -2 or behaving as a -2 oxidation state. We're not going to see it either. Okay, so what about everything else? Well, you would take the things that you know and figure out the thing that you don't know. So I'm going to find the oxidation state or the oxidation number for the carbon atom here. Well, I don't know what it is, so I'll assign it X. That just works. I know what hydrogens are, and I know what they always are, except in those rare exceptions that this is not one of them. And I know what oxygen is, and I know how many there are. So, and I also know that the net sum total of all of those combined give me a neutral molecule. So by the time all of those oxidation numbers are put together, I end up with an overall 0 charge. So that must mean if I solve for X, solve for the one unknown, it has to have an oxidation number of -2. What about something like this? If I start out with one of the polyatomic ions, really the same thing. I don't know what chromium is, so I'm going to assign that an X. I do know what oxygen is, and I know that by the time all of that stuff gets done working out and combining, I have an overall -2 ionic charge on that thing. Which means if I solve for X again, exactly as I did before, I end up with an oxidation state of +6 on the chromium. That's all there is to it. Too easy. Okay, a couple of other important terms, and this is going to make some heads spin. We know that oxidation is a loss of electrons, and you'll sometimes see the acronym LEO for loss of electrons is oxidation. You'll sometimes see the acronym GER for gain of electrons is reduction. You'll sometimes see little rhymes about Leos and said lions and saying GER, but no, whatever. There's two other terms, and they're also quite common. One is an oxidizing agent. Now, an agent is something that makes something happen. So an oxidizing agent causes oxidation. How do you cause oxidation? You cause oxidation by taking electrons away. Well, if you take electrons away, you get reduced, right? So you gained electrons. A reducing agent causes reduction by giving electrons to something else. Well, the thing that gave electrons away lost electrons. So there are going to be some backwards things. So an oxidizing agent gets reduced. At the end of this, and by the time you are comfortable with doing this in class, these are the things you should be able to do with it. This is how we are going to be using this part of redox chemistry. There are going to be more things involved. Just giving you a quick little look ahead. If I'm having electrons move, if I cause those electrons to move through a wire and I give them energy and I put them to work for me, I have an electrical circuit. So a common battery uses redox chemistry. Anyhow, we'll work with this in class and see where we go from there.